Thank you, Gassy. Now I will present next part, related works. We'll cover the following two questions: what neural net quantization is, and what existing frameworks are. As models become more accurate in their prediction and networks get deeper, the amount of memory consumed by neural networks becomes an issue. As we can see in the figure, here are some popular models and their size. Typically, current cell phones are equipped with 4 GB of memory to support multiple applications running simultaneously, and 3 model running ones typically take up 1 GB of memory. So model size is not only a memory capacity issue, but also a bandwidth issue. With network running, memory, GPU, battery will all be consumed at a rapid rate, and we cannot afford to pay such a high price just to make the device a little bit smarter. So what are the benefits the smaller model have? Number 1, smaller storage size. Smaller models occupy less storage space on user devices. And number 2, smaller download size. Smaller models require less time and bandwidth to download users' devices. And number 3, less memory usage. Smaller models use less RAM when they run, which frees up memory for other parts of the application to use and can translate to better performance and stability. As a result, the field of deep learning has devoted significant research resources to this problem in two main areas. On the one hand, designing more efficient network architecture that achieves acceptable accuracy with relatively small model size such as MobileNet and QuizNet. And on the other hand, reduce the network size by compression coding. So, quantification is one of the most widely used compression methods. These two aspects can sometimes be used together and achieve impressive results. For example, the TensorFlow quantized mobile net v1 is only 4.8 MB, which is even smaller than most GIF motion pictures, making it easy to deploy on any mobile platform. As we can see, following type of quantization have chip size reduction and with low accuracy loss. Quantization is a common method to achieve acceleration and compression, and we can divide this quantization into two main categories: code-based quantization and fixed-point quantization. So let's move on to the methods. Mainly, there are four methods: post-training quantization, fixed-point training, binary network, quantized aware training. Even though binary networks have better compression and better performance on adjusting quantization errors, our experiment will focus on if downcast and upcast of weighted quantized networks affect the performance after converting to WebAssembly-based model. Therefore, quantization aware training using low-bit integers is a model architecture that can fit our purpose. There are four major image classification frameworks and 4 backends available in modern browsers. All frameworks support multiple backends, and WebAssembly is one of them. It is worth noting that apart from utilizing WebAssembly backend directly, Apache TVM gives a new method to combine WebAssembly and WebGPU on the web. Even so, it also indicates the potential of WebAssembly on the web. Although WebAssembly is not the latest backend, because it's easy to deploy in nature, it becomes arbitrary. To the best of our knowledge, this is the first study that deployed neural network using pure WebAssembly technology on the web without installing complicated dependency. Let's analyze the existing frameworks. All four mainstream frameworks support WebAssembly. As a result of that, developers must depend on one of them, particularly if researchers want models converted by different frameworks to work together. It is inevitable to download the prerequisite of all frameworks for loading model correctly. Therefore, we will try to save neural networks as pure WebAssembly files and parameter files instead of bonding with specific dependencies. So that's my part, and then Simon We'll present the rest of parts